In this video, we are going to put together all of the things we've learned in the last few sections to create a nice detailed graph of a function. In these problems, to create our graph, we're going to start by finding the domain. Then we'll find all of our asymptotes. Vertical asymptotes occur when you get zeros in the denominator, as long as there isn't a common factor. That's when you'll have a limit that equals infinity. Horizontal asymptotes occur when you take the limit as x goes to infinity. They describe the end behavior. We're going to determine where the function is increasing or decreasing. We'll do this by looking at the first derivative, and that will also tell us where all local min and maxes are. Then we'll find out where the function is concave up and concave down. That's done by looking at the second derivative, and that will give us information about inflection points. Finally, we'll be able to put all this information together to create a graph. So here's an example. We have the function f of x equals 1 minus 3x plus 5x squared minus x to the third. The domain of this function is all real numbers. This is a polynomial. It doesn't have any square roots, no fractions. Domain is all real numbers. Because this is a polynomial, that means it also has no asymptotes. All right, so to figure out where is this function increasing or decreasing, we have to analyze the first derivative. So the derivative would be negative 3 plus 10x minus 3x squared. So there's my derivative. If I want to figure out where the function is increasing or decreasing, I have to find the critical points. To find critical points, I'm going to set my derivative equal to 0. So now I need to solve negative 3x squared plus 10x minus 3 equals 0. I'm going to go ahead and multiply everything by negative 1. I find it easier to solve quadratics if that first term is positive. So 3x squared minus 10x plus 3 equals 0. I'm going to see if I can factor this. If I couldn't factor, I could use a quadratic formula. But 3x squared has to be 3x and 1x. And then that constant 3 tells me I have to have a 1 and a 3. And so let's see, my inner term would be 1x, outer term would be 9x. If I make both of those negative, that does add up to the negative 10x that I need in the middle. So if I set each of those factors to 0, I get two critical points. One at x equal 1/3, and the other at x equal 3. So now I'm going to make a table, and I'm going to analyze the sign of my first derivative to figure out where this function is increasing and decreasing. So I need to pick a test value that is smaller than 1/3. I decided to use 0, so I took x equals 0, and I plugged that into my derivative, and I got negative 3. Because that value is negative, that tells me my derivative is negative everywhere when x is less than 1/3. Then I'm going to pick a number between 1/3 and 3. I chose x equal 1. I took x equal 1, I plugged that into my derivative, and I got f prime equals 4. Because that's a positive number, the derivative will be positive for all x values between 1/3 and 3. And then I pick a number bigger than 3. I chose 4. I plugged 4 into my derivative, and I got negative 11. So the derivative is negative when x is bigger than 3. If we have a negative derivative, the function is decreasing. Positive derivative, the function is increasing. I can see that the function changes from decreasing to increasing at x equal 1/3. So that would be a local min. And the function changes from increasing to decreasing at x equal 3. That's going to be a local max. All right, so putting all of this information together, I know that I have a local min at x equal 1/3. And then I took x equal 1/3 and I plugged it into my original function. To get the y value, I decided to give a decimal approximation because that's going to make it a little bit easier for me to graph. and I got approximately 0.52. So at the point 1/3, 0.5-ish, we have a local min. And then I have a local max at x equal 3. I took 3 and plugged that into my original function, and that gave me a y value of 10. So max is at 3, 10. I can see from my table the function is decreasing from -infinity to 1/3 and from 3 to infinity, and it's increasing in the middle from 1/3 to 3. So we have analyzed our first derivative and gotten a lot of information about increasing, decreasing, max, and mins. Now let's do something similar but with the second derivative. So my second derivative is going to be 10 minus 6x. I'm going to set that equal to 0 and solve for x. I got x equal 10 over 6, or 5/3. So the second derivative is 0 when x is 5/3. I'm going to create my table and now analyze the sign of the second derivative. I chose a test value that's smaller than 5/3. I chose 0, and I plugged that into my second derivative, and that gave me 10. That's a positive value. Second derivative is positive means the function is concave up. Then I picked a number bigger than 5/3. I chose 2. I plugged that into my second derivative and got -2. That means the second derivative is negative when x is bigger than 5/3. Negative second derivative means the function is concave down. I can see that there's a change in concavity at x equal 5/3, so that's going to be an inflection point. So I'm going to jot down all of that information, inflection point at 5/3, and then I took that 5/3, I plugged that into the original function, and got approximately 5.26. So there's my inflection point. The function is concave up from -infinity to 5/3, and it's concave down from 5/3 to infinity. All right, so we have completed our analysis. We have looked at the domain, all real numbers, asymptotes, there aren't any. We analyzed our first derivative, and then we analyzed our second derivative. So now finally we're ready to put all of this information together into a really nice graph of this function. So when creating a graph by hand, the first thing I'm going to do is plot any points that I have found. So I have a total of 3 points that I have found: a min, a max, and an inflection point. So I'm going to start by graphing those 3 points. So I had to just kind of estimate. My min was at 1/3, like 0.5. My inflection point is at 1 2/3, and then 5 point something. And my max is at 310. And then I'm going to go through and connect the dots, looking at the information I have found about whether the function is increasing or decreasing. So basically, I'm going to look at each region between these points, these dots, and figure out how to draw the curve, how to connect the dots based on what I've already done in terms of increasing, decreasing, and concavity. So when x is less than 1/3, from -infinity to 1/3, when x is less than 1/3, the function is decreasing and concave up. So I have drawn something on the right, I guess this is the left side of the graph, that is decreasing, going down, but has that upward curvature. Then from x equal 1/3 to x equal 5/3, now the function is increasing. Once we get bigger than 1/3, which is where our min occurs, the function starts increasing. But we're still going to be concave up. We don't flip to concave down until we get past that 5/3. So I'm going to draw something that's both increasing and concave up. So we still have that upward concavity, but now it is increasing. Then I'm at x equal 5/3. At x equal 5/3, that's where the concavity changes. So it's going to flip from concave up to concave down. When x is 5/3, we're still in this increasing interval. It's not going to switch to decreasing until we get to x equal 3. So from 5/3 to 3, we are increasing and concave up. So I think I said that wrong. Increasing definitely, but once we're bigger than x equal 5/3, concave down. So increasing, concave down, I've sketched that on my graph. And then finally on the right side, once I'm at x values that are bigger than 3, now we are decreasing again, and we're still going to be concave down. So I have drawn something that's decreasing and concave down. And there's a really nice sketch of this polynomial that does include all of those important features. Let's take a look at another example. We have the function f of x equals x divided by x squared minus 9. To find my domain, I need to look at the denominator. This is a rational function, and the denominator can't equal 0. So x squared minus 9 can be factored as x plus 3, x minus 3. That has zeros at -3 and +3. So my domain is all numbers except for +3 or -3. Vertical asymptotes are going to occur at those zeros of the denominator. There are no common factors, so my vertical asymptotes are going to occur at x equal -3 and x equal 3. To find my horizontal asymptote, I can take the limit as x goes to infinity of this function. If I were to just plug in the infinity, I would get infinity over infinity. That's indeterminate. So I'm going to divide everything by that largest power of x. I'm going to divide everything by x squared. If I divide the top by x squared, that's x over x squared, that is going to reduce to 1 over x. In the denominator, we have x squared divided by x squared. That reduces to 1. And then minus 9 over x squared. Finally, I plug the infinity in. And anytime we have a finite number divided by infinity, that's going to go to 0. So I'm left with 0 divided by 1 minus 0. And 0 divided by 1 is 0. That means the horizontal asymptote is y equals 0. All right, now we are ready to analyze our derivatives. So we're going to have to find the first derivative, and that's going to give us information about increasing and decreasing. I'm going to use the quotient rule to find my derivative. The numerator, the f, is x. The bottom, the g, is x squared minus 9. So f prime is 1, and g prime is 2x. Putting this into my quotient rule, I take f prime times g, so 1 times x squared minus 9, minus g prime times f, minus 2x times x, all over g squared. That becomes x squared minus 9 minus 2x squared divided by x squared minus 9 squared. Combine like terms, we're left with negative x squared minus 9 over x squared minus 9 quantity squared. To find my critical points, I'm going to set this equal to 0. The only way a fraction will equal 0 is if the numerator equals 0. So negative x squared minus 9 equals 0. If we try to isolate the x squared, we end up getting x squared equals negative 9. But that's not possible. When you square a number, you always get a positive. So this tells me that this function has no critical points. So there are no critical points. However, it's possible that f prime could change sign at the zeros of the denominator. The zeros of the denominator are technically places where the derivative doesn't exist. They're not actually critical points because they're not in the domain of the function. But if we look at that denominator is going to equal 0 when x equals -3 or +3. So I'm going to make my table and figure out what is the sign of the derivative when x is smaller than -3, when x is between -3 and 3, and when x is bigger than 3. I did this by using test values. So I took -4, that's smaller than -3, and I plugged that into my derivative. I used a calculator to help me. I ended up getting a negative value. then I took x equals 0, that's between -3 and 3, and I plugged that into my derivative. That also gave me a negative value. And then finally, I picked something bigger than 3. I chose 4. I plugged that into my derivative. Once again, I got a negative value. So this tells me that the function is always decreasing. So this function is always decreasing. There were no critical points, so there are no maxes and mins. So we have no local maxes and mins, and the function is decreasing from -infinity to -3, -3 to 3, and 3 to infinity. All right, let's take a look at our second derivative. So I'm going to take the derivative of my derivative. I'm going to have to use the quotient rule again. F is -x squared minus 9, and g is the quantity x squared minus 9 squared. So f prime is -2x. G prime, I'm going to use the chain rule. So I brought down the 2 times x squared minus 9, and then I have to multiply by the derivative of the inside. The inside is this x squared minus 9, which has a derivative of 2x. All right, so putting this into my quotient rule, f prime times g minus g prime times f all over g squared. So -2x times x squared minus 9 squared minus 2 times x squared minus 9 times 2x times -x squared minus 9 all over x squared minus 9 squared squared. All right, we're going to do some algebra on this. And I'm going to start by trying to factor the numerator. So for the numerator, I have a common factor, both of these terms in the numerator. So I'm comparing the two things that are being subtracted in the numerator. They both have a -2x. Here's a -2x. So I'm going to take a -2x out of both of these. And they both also have a factor of x squared minus 9. X squared minus 9. So I'm going to take -2x, x squared minus 9 out of both of these terms. In the first term, if I pull out the -2x and one of the x squared minus 9s, see how there's a squared there, there's going to be one left over. So I'm going to have 1 x squared minus 9 left over. Now I'm going to look at that second term. I'm taking out the negative here. So I'm taking out the negative, the 2x, and the x squared minus 9. That means I'm going to be left with this minus here is going to become a plus. I'm left with this 2 in front. I haven't taken that out. I took out the x squared minus 9. I took out the 2x. I'm left with a -x squared minus 9. So I have factored the numerator. And then in the denominator, 2 times 2 is 4. So I can write that as x squared minus 9 to the 4th. Let's do some more algebra. There is a common factor of x squared minus 9. So I'm going to start by canceling that out. Common factor of x squared minus 9. Then in the parentheses, I'm going to distribute this 2 to the -x squared minus 9. So my numerator, we still have that -2x left. And then times x squared minus 9 minus 2x squared minus 18 all over x squared minus 9 to the 3rd. Combine like terms. 1x squared minus 2x squared is minus x squared. Minus 9 minus 18 is minus 27. So my second derivative, and I just noticed, I'm sorry, I only had an f prime on this. We're actually computing our second derivative. So my second derivative, f double prime, is -2x times -x squared minus 27 all over x squared minus 9 to the 3rd. I'm going to figure out where does this second derivative equal 0. The only way a fraction can equal 0 is if the numerator equals 0. So negative 2x equals 0 has a solution of x equals 0. Negative x squared minus 27, that's never going to equal 0. This reminds me of when we worked with the first derivative. We isolate the x squared, we get x squared equals a negative number. That doesn't have any real solutions. So I have only one place where the second derivative is 0, and that occurs at x equals 0. Now when we analyze the sign of the second derivative, we also need to include zeros of the denominator, for the same reason we included them when we analyzed the first derivative. Zeros of the denominator are places where that derivative is undefined. There are also places where we have vertical asymptotes, so the graph could change concavity at those locations. So when I make my table, I need to include x equals 0. That's a place where my second derivative equals 0, and x equal negative 3 and 3. Those are places where my second derivative is undefined. Those are also numbers that are not in the domain of my function. So once again, we'll use test values. I chose negative 4. I plugged that into my second derivative, and I got a negative answer. So that tells me the function is concave down. Then I chose negative 1 as my test value between negative 3 and 0. I plugged that into my second derivative and got a positive value. There, the function is concave up. From 0 to 3, my test value was 1. I plugged that into my second derivative. I got a negative, so concave down. And then finally, bigger than 3, I chose 4. Put that into my second derivative. I got a positive, so concave up. So I know where the graph is concave up and concave down. I'm going to have an inflection point at x equals 0. The function changes concavity at x equals 0. If I take 0 and I plug that into my original function, I get a y value of 0. So my inflection point is at the origin. X equal negative 3 and x equal positive 3 are not inflection points because they're not in the domain of this function. They aren't points on the graph, they're actually asymptotes. But the graph does change concavity at those locations as well. So it's concave up from negative 3 to 0, and from 3 to infinity, and concave down from negative infinity to negative 3, and from 0 to 3. All right, so let's put all of this information together and try to sketch a graph. So first thing I'm going to do is draw any points that I have found, and I have found only one point. That's my inflection point at the origin. So I am going to plot that point at the origin. I'm also going to plot any asymptotes. We have a vertical asymptote of x equal negative 3 and another one at x equal positive 3. So I've very lightly put in some dotted lines to indicate that x equal 3 and negative 3 are asymptotes. I have a horizontal asymptote of y equals 0. So I'm going to really lightly draw in a horizontal line, y equals 0. And I like to do that just at the ends of the graph, because horizontal asymptotes only impact the end behavior. They don't tell you what's happening in the middle of the graph. So I drew in my horizontal asymptote at the ends of the graph. And now we're going to try to connect the dots. I guess we only have one dot though. So let's just start by the middle, because that's where our one point is, and see if we can figure out how to draw this function with the information we have. So when x is less than 0, when I'm between negative 3 and 0, looking at the information on my screen, between negative 3 and 0, the function is concave up and it's decreasing. This function is actually always decreasing. So I'm going to draw something that is concave up and decreasing. So here it is, decreasing down, but concave up. Then, between x equals 0 and x equals 3, the function is now concave down. That x equals 0, the point at the origin, is an inflection point. The function is still decreasing, but it changes from concave up to concave down. All right, now we have to do the right side and the left side. And this is a little bit trickier because we don't have any points to work with. So if you want, you could Just pick any x value smaller than -3 and plot a point just to help you guide your graph. I'm going to show you how I could do it without a point. So I know that the function is concave down, and decreasing. And so if I draw my concave down and decreasing graph all the way up here above my x-axis, I'm not going to be able to get that horizontal asymptote. This function has to be approaching y = 0 on the left side. So that means I could actually start my curve, really kind of approaching that horizontal asymptote, and then I can draw something that's concave down and decreasing. I can use similar reasoning on the right side. I know at the right side of the graph we have to be approaching that horizontal asymptote of y = 0, but the function has to be decreasing and concave up. So I've drawn something that is decreasing and concave up and approaching that asymptote. The other thing I didn't mention when I was drawing this is I did make sure when I was drawing my curves to make sure that we are also approaching our vertical asymptotes. So I do have this drawn so that I'm approaching the vertical asymptotes and the horizontal asymptote. I'm going to stop this video here. Please let me know if you have any questions. I've got some other resources posted as well if you want to see some additional examples. But please reach out if anything in this video is unclear.